Section 1.1 Functions. So first we need to define this thing called a relation. And so a relation is a correspondence between two sets. When we say correspondence, I just mean connected somehow. So a relation is just a connection between two things. The set of all inputs for a relation is called the domain of that relation, and the set of all outputs is called the range. You could think of a relation as a microwave. That is, if you have some input, and let's say that input is some ramen noodles, then if you put that in the microwave with the appropriate amount of water, then you're going to get some cheap dinner. Okay, and so you have an input, the relation changes a thing, and then you get an output. Then we get these things called functions. And so in a function, each element in the domain corresponds to exactly one element in the range. And so a function is a correspondence. It is a relation. But it's a specific type of relation where, once again, what's written here is true. Now there are lots of ways to represent functions, such as mappings, ordered pairs, graphs. We're going to look at all of them. So these are mappings. That is, you have some input on the left, some output on the right, and the arrow is showing you the correspondence. And so in each of the following, we want to state the domain, state the range, and then figure out, does the relation represent a function? Well, the domain is just the inputs, and the inputs here are the gas stations. Now when we write domains and ranges, you're going to want to use what's called a curly brace, and a curly brace is just a way to indicate a set. And so it's the set that is including Shell, Valero, Texaco, and Chevron. Then we close the curly brace, and this is the set that is the domain. Then when you state the range, you do the exact same thing. Write curly braces, but now you're going to write the outputs instead of the inputs. And so the outputs are $2.89, $2.69, $2.49. Of course, close our set brace, our curly brace. So then we ask ourselves, does the relation represent a function? Well, the trick here is you just need to double check and make sure that no inputs repeat. And that's really the easier way to consider this. Is it a function? If there's no repeating inputs, then yes it is. And so I see Shell, Valero, Texaco, Chevron, and each one of those has exactly one output. And since that's the case, yes, this mapping represents a function. Our next mapping, we want to do the same. So this is carats related to price when talking about diamonds. And so first, let's state the domain, curly brace. So the carats are 0.70, 0.71, 0.75, 0.78. That is our set of inputs, the domain. Then we state the range. The range outputs at 1,529, 1,575, 1,765, 1,798, 1,952. So that's the range, those are the outputs. Now let's figure out, does this relation represent a function? Remember, each input will correspond to exactly one output. But notice that right here, there's this arrow coming from 0.71 carats, and it's going to two outputs. And so we know this is not a function because the input is ending up repeating, or it goes to two outputs. We can also think of a relation graphically, or as a set of ordered pairs, and the truth is these two things end up being close to the same thing. The graph includes all the ordered pairs that occur with some function. And so the domain, though, being the inputs, we're usually going to think of those as the x values. And then the function acts on it, and we get to the outputs, and that's going to give us the y values. And so usually domain will be x, and range will be y. A relation is a function if the elements in the domain do not repeat. So this repeats back what I said earlier. That's the whole deal. If the domain elements do not repeat, then we can say that a relation is a function. If neither the domain nor the range repeat, then we're going to call that type of function a one-to-one function. So we're going to state the domain and range for the following relations, and then determine if the relation represents a function. So let's deal with this first one. And I'm going to represent the domain. Well, I just need to find the x values. And so notice I have 4, -9, 9, and 4. Because we're talking about a set in curly braces, if something repeats, it doesn't matter, you're only going to write it once. So even though 4 shows up twice, we just write 4 one time. then we also have 9 and negative 9 showing up. That's all that shows up. That's our domain. Then let's refer to our range. Our range is just the y values. So we have 8, 8, 10, and 12, but since 8 repeats, we only write it once. So 8, 10, and 12, that's our range. And then we need to answer the question, does it represent a function? Well, do any of the x values repeat? 4 and 4 repeats, right? So this thing is not a function. Then, next one, let's do the domain of this set of ordered pairs. So -4, -3, 1, and 5. Then the range values, 8, 1, 0, and -3. Let's ask ourselves, is this thing a function? And so look, none of the x values repeat, and since none of the x values repeat, we can say that yes, it's a function. One more thing when we're talking about sets and curly braces, so we never write repeats, and then the other thing is that the order in which you write things into a set doesn't matter. If you decide and you get into the habit when you write sets to write things in numerical order, it'll probably help keep you on track better, but it's not a requirement. Functions will often be denoted by some letters. Usually we're going to use lowercase or uppercase F's or G's, but there's nothing wrong with H's or any other letter that you so choose. You could always use Greek letters to represent a function. Now if f is a function, then for each number x in its domain, the corresponding image in the range is denoted by the symbol f of x. So for the function y equals f of x, now x is called the independent variable or the argument, and then y or f of x is called the dependent variable, and that's because y will depend upon the x value. Another way you can think about a function is as a machine, and so as a machine it's only going to accept elements from the domain. If you have some function and you're trying to plug something into it that's not in the domain, it doesn't understand how to work with it. And once you plug in values that are actually in the domain, there's only going to be one output for that x value. Now it could be repeated. The outputs can repeat, but the x value will only correspond to exactly one output. And so if we say f of x is equal to x cubed, that means whatever your input is, you just cube it. And so f of a means cube of the a. That's all. So now we just want to find function values. If we're finding function values, all you need to do is replace whatever's in the parentheses with whatever's in the next parentheses. So we have f of x. So everywhere we see x, I'm going to put parentheses, and I'm just going to put into the red parentheses whatever is in this thing here. So f of 2 is really 2 times 2 squared plus 2 minus 5. Well, then 2 squared is 4. So this is 2 times 4 plus 2 minus 5, which is then 8 plus 2 minus 5, which is 10 minus 5, and 5. So that is the value of f of 2. And you can write f of 2 is equal to 5. Well, I also want to address that since we've plugged in values for functions, understand that this also indicates an ordered pair. And that ordered pair is the x value that got plugged in, which is 2, and the y value that got spit out, which is 5. And so these two things really mean the exact same thing. F of 2 is 5 means the ordered pair 2, 5. If I just want to plug in something like negative x, well, we just put inside the red parentheses above this negative x. So 2 times negative x quantity squared plus negative x minus 5. And then simplify as much as you can. This is then going to be 2. Negative x quantity squared is really negative x times negative x, but that's going to be positive x squared, so that's x squared. Plus a negative, I'm just going to write that as minus x minus 5, and so that is my answer. F of 3x, same idea. 2 times 3x in parentheses quantity squared plus 3x minus 5, and then let's clean it up some. So 3x quantity squared is 3x times 3x, which is going to be 9x squared, and so that's 2 times 9x squared plus 3x minus 5. 2 times 9 is 18, and x squared plus 3x minus 5. Finding more function values. Now notice that I have negative f of x. Well, negative f of x is really just a negative in front of the entire function. And so if this is all of f of x, that's what this is. Just put a negative in front of it. Negative 2x squared plus x minus 5. Distribute. This is then negative 2x squared minus x plus 5. There's our function value. And now if I want to plug in a binomial into a function, there's no reason I can't. This is then f of x plus 2, which is, everywhere we see x, we replace it with parentheses, and this is going to be 2 times x plus 2 quantity squared plus x plus 2 minus 5. Then I have 2 times x plus 2 quantity squared. Well, this is a binomial squared. So remember that x plus 2 quantity squared is x plus 2 times x plus 2. And so we need to multiply those binomials. So this is 2 times x squared plus 2x plus 2x plus 4 plus x plus 2 minus 5. That's then going to give us 2 times x squared plus 4x plus 4 plus x minus 3. And then distribute, that's then going to give us 2x squared plus 8x plus 8 plus x minus 3. Combine like terms again. I'm left with 2x squared plus 9x plus 5. Now the binomial is just changing. It's just going to be all variables. So f of x plus h will look very similar to the last, except this is just going to be, everywhere we see the x, replace it with parentheses. This is then 2 times x plus h quantity squared plus x plus h minus 5. That's then going to be 2 times x squared plus x times h plus x times h plus h squared plus x plus h minus 5. Clean up this x times h. That's going to be 2 times squared plus 2xh plus h squared plus x plus h minus 5. Then that's going to give us 2x squared plus 4xh plus 2h squared plus x plus h minus 5. So I have no other like terms that I can combine. Same trend, different looking function. So now we're trying to find f of x, where our function is a rational expression. Replace our x with the value getting plugged in. F of 2 is then 3 times 2 plus 5 divided by 5 times 2 minus 7. That's equal to 6 plus 5 divided by 10 minus 7. 6 plus 5 is 11. 10 minus 7 is 3. 11 thirds. Double check to make sure it won't simplify, but 11 and 3 are relatively prime. That is, they don't have a common factor, so they won't reduce. F of negative x is going to be 3 times negative x plus 5 divided by 5 times negative x minus 7. That is, just to clean it up, negative 3x plus 5 divided by negative 5x minus 7. F of 3x, that is 3 times 3x plus 5, all divided by 5 times 3x minus 7. 3 times 3 is 9, so that's 9x plus 5 divided by 15x minus 7, and we're done. Once again, if I have negative on the outside, it's just negative on the outside of the entire function. Because this is a rational expression, there's at least 3 ways we can write this differently, but they're all going to be the same. So I'm going to show you all 3 ways. This is then going to be negative 3x plus 5 divided by 5x minus 7. And so when you have rational expressions or fractions, if you want to write the negative just out front in front of the fraction bar, that's okay. But realize that if you decide to place it on top or on bottom, you must put parentheses around the top or the bottom, wherever the negative is, to understand that it must be distributed. And so I can write this like this, and that's okay. Of course, because I can write it like that, I can also then distribute that negative, and that's negative 3x minus 5 divided by 5x minus 7. Alternatively, you could put the negative on bottom with parentheses, and then you can distribute that negative, which would also give you the choice of 3x plus 5 divided by negative 5x plus 7. And so notice that this solution, this solution, this solution, and this solution are all equally good. It's just a matter of preference. Now we're just going to input binomials into the function. So 3 of x, 3 times x, and 5 times x. I just need to put the parentheses around the x's so that I can replace them. Then that's going to give me 3 times x plus 2 plus 5 divided by 5 times x plus 2 minus 7. So we can clean it up some. That is 3x plus 6 plus 5 divided by 5x plus 10 minus 7. Or 6 plus 5 is 11, so that's 3x plus 11 divided by 5x plus 3. F of x plus h, same theme. 3 times x plus h plus 5 divided by 5 times x plus h minus 7. Distribute the 3. 3x plus 3h plus 5 divided by 5x plus 5h minus 7. And we're done. So now we're going to talk about the difference quotient. And understand that for us, for all intent and purpose, it's just a formula that you need to be able to use and simplify. That's all. But I'm going to explain it so that when you get to calculus, or if you decide to take calculus, you'll at least have seen it once. But the difference quotient can really do this interesting thing where we can approximate the slope of a line under certain circumstances. And so let's just walk through this setup. So first off, we have a graph, that function f of x. Now let's say I start at a point. I'm going to start at the point x f of x. Then what happens? Well, we're going to walk a little bit down the x-axis. We're going to go to a distance of x plus h. So we're going to move a little bit of distance h, and then we get a new point x plus h. Well, because we have a function value x plus h that can be plugged in, we get an output that's just going to be f of x plus h. So now we have two ordered pairs. Then the idea is we want to approximate the slope. And so let's just think about slope. Let's connect the two dots. Connect the two dots, and then we have a slope formula. Rise over run, change in y over change in x. So we just take those y and x values. F of x plus h minus f of x divided by x plus h minus x. Well, then you can simplify. Well, when you simplify this is really x minus x, and those cancel. And so you're really left with f of x plus h minus f of x over h. This is what we mean when we say difference quotient. It's just a formula. F of x plus h minus f of x divided by h. That's all. Then, if you know that h gets small enough, which is what happens in calculus, then you can approximate the slope of a curved line. And that's the idea. Now let's try it. We want to find the difference quotient of f of x is equal to 2x squared plus x minus 5. Well, the formula for difference quotient is just f of x plus h minus f of x divided by h. We know what f of x is. There it is. We also know what f of x plus h is because we calculated it just a little bit ago. So f of x plus h is really equal to 2x squared plus 4xh plus 2h squared plus x plus h minus 5. And so that's the work that we did earlier. We just plugged in x plus h into the function, and then we simplified it. So then we just have f of x plus h minus f of x divided by h. So let's write that out. F of x plus h. Well, f of x plus h is all of this. So that's going to be 2x squared plus 4xh plus 2h squared plus h plus x plus h minus 5 minus the function f of x. Well, that's just 2x squared plus x minus 5. Do make sure you put parentheses around the function because we're going to need to distribute that negative. And that's going to be all divided by h. So this then gives us 2x squared plus 4xh plus 2h squared plus x plus h minus 5 minus 2x squared minus x plus 5, all divided by h. Then let's look and see what like terms can be combined. So I see, first off, I see 5 and negative 5. So minus 5 plus 5, that gives me 0, so those cancel out. I also see plus x minus x, those cancel out. I see minus 2x squared plus 2x squared, those cancel out. And then notice that I'm just left with this h stuff. And so that's going to leave me with 4xh plus 2h squared plus h, all divided by h. Then, one of two ways to work with this. Because it's fraction addition, you could break up each term in the numerator over the denominator. 4x times h over h plus 2h squared over h plus h over h, and then you can reduce each fraction. Or you could pull out a greatest common factor. That greatest common factor is h times 4x plus 2h plus 1 divided by h divided by h is 1, and so then we're left with 4x plus 2h plus 1. And that is the difference quotient. Now we're going to talk about this thing called interval notation. And so interval notation allows for us to write large amounts of real numbers without exerting a lot of effort. And so specifically, first let's start with the definitions. Let's say that I want to talk about all real numbers between two numbers a and b, and I want to include a and b. So what does this mean? Well, first let's talk about the interval. Well, the way we're going to write the interval, we're either going to use a parentheses or a bracket to indicate including or not including. Parentheses will mean not include, a square bracket will mean include. And so the interval here is including a and b. It's going to be square bracket a up to b, square bracket. And that means exactly what's written here. All real numbers between a and b, including a and b. Well, you can also write this as an inequality. Well, what's that inequality going to look like? Well, it's going to be a is less than or equal to x is less than or equal to b. And so it's the same idea as saying, oh, well, x is trapped between a and b. It could be any of the numbers in there. It could also be a. It could also be b. Then we can also graph it on a line. And I hope you've seen this before, but if not, that's okay. And we're going to say that there's really two linear graphs of this, and I'm going to show you which one MyLabs likes. But they look like this. So if you remember making solid dots to indicate included and then the line in between, there you go. But we're going to change it up a little bit, and we're going to actually match the interval notation, and instead of using a closed circle, we're actually going to use a square bracket when we mean to include it. So your linear graphs will match your interval notation. So now our definition for the interval notation we want to talk about is all real numbers between a and b, excluding a and b. So it's very similar to the last, except a and b are not included. So the interval here is going to use parentheses on both ends. It just says everything between a and b except a or b. Then the inequality is going to be a strictly less than x is strictly less than b. And then the graphs will be an open circle on the endpoints because those points aren't included. Or the way you're going to need to graph it in MyLabs is with an open parentheses that means the exact same thing as the open circle. Don't include the endpoints, but do include everything in between. Change it up a little. All real numbers between a and b. We're going to exclude a, but we're going to include b. Exclude is parentheses. Include is a bracket. So this is parentheses a, b, square bracket. The inequality is then a is strictly less than x, which is less than or equal to b. And then for our graphs, we're going to have an open circle on a, closed circle on b, or make it match the interval notation, that is parentheses on a, square bracket on b. All real numbers between a and b, including a but excluding b, just swapping it around. The interval is square bracket a, b, parentheses. The inequality is a is less than or equal to x less than b. And then our graph is going to be a closed circle on the left, open circle on the right. And then, or you could use a square bracket on the a and a parentheses on the b. When dealing with interval notation, understand that you can never include the values negative infinity or infinity. And when I say include, I mean it's not really a number. Infinity and negative infinity are really ideas. They are a thing that is larger than everything that's a real number or smaller than everything that's a real number. And therefore, anytime we use them in interval notation, you will always use a parentheses on infinities. So now we're just going to fill out the chart by making sure that everything we just talked about matches. And so we're given an inequality here. Negative 4 strictly less than x, less than or equal to 0. It's your choice if you want to do the graph first or the interval first. In general, you should just be able to flow between all three viewing options. So if I see the inequality -4 strictly less than x less than or equal to 0, -4 and 0 are my endpoints, and then because of the strict inequalities, I'll use parentheses, and when I have an equal sign, I'll use a bracket. And if it helps you remember, the equal sign is flat, the bracket is flat, that's where they go. So this is then parentheses -4 up to 0, close bracket. When you're writing interval notation and you're writing the intervals, the order in which you write the numbers matter. You will always have the most negative thing on the left and the most positive thing on the right. And just remember that means that if I'm going from left to right like a number line, you just want your numbers to match the number line reading left to right. Then to graph this, we do not include -4, so that's a parentheses on -4. And then it goes to the right all the way up to 0, but 0 is included, so it's going to get a square bracket. And so our graph looks like this. Then we have from -infinity to 2. Well, what does that mean? That means we go as far left as possible. Once again, notice I put parentheses on -infinity because it's not a number, but it's everything up to 2, including 2. Well, that's really saying that the x value is less than or equal to 2. It could be anything to the left of 2, including 2. And so when I graph this, I just have a square bracket on 2 and everything to the left. When working with the inequalities to go back and forth between the different notations, if you have your letter, your variable on the left, the arrow will point in the correct direction. Okay, so I know that the ones where the x is trapped, you got to be a little bit careful. But if ever you've got just from infinity to some number or from some number to infinity, this arrow will line up. So now let's look at our next one. We're starting with the graph. This thing, well, is between -8 and -10. Each one of these appears to be a tick mark of 1, so this is really the value -9. And so we start at -9, but since it's a parentheses, it's not included, and it goes to the right. And so that's really like saying x is greater than, strictly greater than, because of a parentheses, -9, which in interval notation is parentheses -9, and it goes forever to the right, so it goes to infinity, and then parentheses because infinities get parentheses. Now I have from -infinity to +infinity. Well, -infinity to +infinity is really everything. So that's going to be all real numbers. Usually we don't write this as an inequality. If you ever saw -infinity less than x less than infinity, maybe it's okay, but that's usually not what we write. This is actually going to be a way that we say all real numbers. All real numbers can be written with a double script R, but that is the exact same thing as saying all reals or all real numbers. And then the graph of this is just the whole line. So my lines just go forever in both directions, and so I'm going to use arrows to indicate that it just keeps on going and covers all of the real line. Now that we've talked about interval notation, let's figure out why we care. Well, that's when we're talking about domains. And so usually when we talk about the graph of a function, we're going to determine the domain and range. If you have the graph, the image, you can do it visually. And we're going to do that later sometimes. But right now we're going to do it algebraically. And so when we're talking about this, it's going to be actually easier to think about when can we not have a value in the domain over what is in the domain. And the reason I say that is that there's a limited number of ways that things fail for the domain. Let's list those. That is division by 0. You can't do it. And so in general, if you ever have a rational expression, if you're worried about the domain restrictions, you just have to say, oh, well, I know that I can't divide by 0, so I'm going to set whatever's in the denominator equal to 0 and say, well, I know that can't be the case, and then figure out what would make that happen, and those values I'm going to kick out. The other situation is going to be even indexed radicals, or even roots. And so square root, fourth root, sixth root. The big deal is that when you take even indexed radicals of numbers, we don't have a way currently, at least we're not going to deal with it right now, how to find the square root, fourth root, sixth root of negative numbers. And so everything in the radicals is going to have to be the situation where the stuff inside an even index radical is greater than or equal to 0. So now let's actually find the domain of each of the following functions. And once again, you're looking for two things. You're looking for division by a variable or even index radicals. If you don't see those things, then you probably don't have a domain restriction. And so notice that for this first function, I've got negative 2x plus 7. Well, do we have any division by a variable? No. Do we have any even index radicals? No. And so when I find the domain of this first one, the domain of this first one is just going to be all real numbers. There are no problems, no issues, so the domain is everything. Anything we want to plug into this function, we can plug into this function and the output will make sense. Then I've got this next one, f of x is equal to 3x divided by x squared minus 6x minus 7. Do we have division by variables? Yes. This is a division bar. Fractions are division bars. And so when I'm trying to find the domain, I need to just say, well, I know that the denominator cannot be 0. And so since this thing cannot be 0, I need to kick out those values. So we need to really solve this equation. X squared minus 6x minus 7 factors into x minus 7 times x plus 1. We know that can equal 0. Then I use the zero product property, and that's going to be x minus 7 cannot equal 0. X plus 1 cannot equal 0. X cannot equal 7. X cannot equal negative 1. And so those two values get kicked out. So we need to write everything else except those two values. So if it helps you, you could graph this on a number line, put open circles at 7 and negative 1, and then write everything else. So now the domain is going to be from negative infinity up to negative 1, not including, union, not including negative 1, up to 7, not including, union, not including 7, up to infinity. Then moving on to this last function, notice, do we have any division by variables? Yes, we have division by x squared plus 4, and so we need to check that. So we say x squared plus 4 cannot equal 0. Solve it, that's minus 4 minus 4. X squared cannot equal negative 4. But then you can try to take the square root of it, but right now when we talk about taking the square root of a negative, that's not a real number. And since that's not a real number, I know that that's actually not a problem because there's never a situation where the denominator here will be 0. And so since this is not a problem, this is then going to be all real numbers. There's no domain restrictions for this one. And so the domain for this one is from negative infinity to positive infinity. Now we have even index radicals. So we want to find the domain of each. And so if we have g of t is equal to the square root of 5t plus 15, the thing to recall is that this is a square root, so it's an even index radical. And what matters is that everything inside the radical has to be bigger than or equal to 0. Because the square root of 0 is just 0, and that's okay. But the square root of negative numbers don't work for us. So that is 5t plus 15 must be greater than or equal to 0. Then we can solve for t. So minus 15 minus 15. 5t is greater than or equal to negative 15. Divide by 5, divide by 5. T is greater than or equal to negative 3, which in interval notation is including negative 3 all the way up to infinity. And so that will be our domain. Anything outside of that can't be plugged into our function. Then we look at f of a. F of a has the square root of 3a plus 9, but notice that it also has division by a variable. So this is going to be a little bit extra work, but that's okay. That's what we have to do. So first thing is I know that a minus 4 cannot equal 0, and I also know that 3a plus 9 has to be greater than or equal to 0. Those two things have to be true. So a cannot equal, add 4 to both sides, a cannot equal 4. Then 3a plus 9, solve it, minus 9 minus 9. 3a is greater than or equal to negative 9. If I divide by 3, divide by 3, a is greater than or equal to negative 3. And so notice this is something weird, and if you actually wanted to do this on a number line to help keep yourself on track, if negative 3 is here and 4 is here, what does that look like? Well, we're going to exclude 4. So an open circle on 4. Then we have an equality on -3, and it goes to the right. Now, if I wanted to replace that circle with the parentheses, it would actually look like this, because 4 is excluded. And so when I write this interval, what does that interval look like? That interval is starting with -3 including, up to 4 excluding, union 4 up to infinity. Lastly, I have 9t divided by the square root of t minus 2. So this is really a twofold problem as well. This is a square root that's also in the denominator. And so just if we deal with the even index radical part, we would say that t minus 2 has to be greater than or equal to 0. That's the radical part. But we also know that the denominator can't equal 0, and the only way you get 0 in the denominator is if you got the square root of 0. So I'm just going to move the equal sign off, saying, oh, well, I know it can't be equal to 0, and this will take care of my problems. So now I have t minus 2 is greater than 0, add 2 to both sides, and so I get t is strictly greater than 2, and so my domain for this one is excluding 2 all the way to infinity. Now, given two functions, f of x and g of x, where x is in the domain of each, we're going to have a couple situations that occur. Well, we're going to be able to add functions. That is, if you want to add and subtract functions, that's fine. And so that notation is going to look like this. F plus or minus g of x is really the same thing as f of x plus or minus g of x. They also have a product. F times g of x is the same thing as the function f of x times the function g of x. We also have quotient. That is, f divided by g of x is the same thing as the function f of x divided by g of x, where very specifically your denominator cannot be 0. When we do algebra with functions, adding, subtracting, multiplying, the deal is that the new domain will always be the intersection of the other functions. And so intersection means where do those domains overlap, and that's written the domain of f intersects the domain of g. Now, when we have f divided by g, we have one more thing we have to be concerned about. So first off, we have the domain of f intersect the domain of g, but then we must pull out any of the x values that would have caused g to be 0, because of course division by 0 doesn't work. So let's find domains. And if I want to do this using the intersection, it's probably easier just to find the domain of f and find the domain of g, and then we'll see where we go from there. So what is the domain of f? Well, the domain of f is 6x plus 1. Do we have any division by variable? No. Do we have any even index radicals? No. Since we don't have either of those, the domain of f is going to be all real numbers. Negative infinity to positive infinity. Everything is included. Then look at g of x. G of x is 2x plus 3. So what's the domain of g? No division by variables, no even index radicals. So the domain of g will also be all real numbers. F plus g is 6x plus 1 plus 2x plus 3. Since it's all addition, the parentheses just drop and you can combine like terms. 6x plus 2x is 8x. 1 plus 3 is 4. 8x plus 4 is that function. And the domain is the intersection of the domain of f and the domain of g. Well, if I have all real numbers, and I ask where they overlap everywhere, very explicitly, negative infinity to positive infinity. Now I want to find the function f minus g, so that is f, 6x plus 1, minus g, that is 2x plus 3. But now we have a subtraction symbol, so we need to distribute. That's 6x plus 1 minus 2x minus 3. Combine like terms, 6x minus 2x is 4x, 1 minus 3 is negative 2. Then when we deal with the domain, it's exactly the same discussion we just had, and so the overlap of all real numbers is all real numbers. So that is from negative infinity up to positive infinity. Now let's find product. F times g, that's just 6x plus 1, times 2x plus 3, which then gives you, multiply the binomials, 12x squared plus 18x plus 2x plus 3. Combine like terms as much as possible. That gives us 12x squared plus 20x plus 3. And then the domain for f times g is the same as f plus g and f minus g. That is the intersection between f and g, and that's going to be all real numbers again. Now we have f divided by g. So f divided by g is just 6x plus 1 divided by 2x plus 3. This function won't reduce, so that's it. Then when we deal with the domain, it's going to be, look at the domains we found above for f plus, f minus, and f times g. And then that was, remember, the intersections of the domain of f and the domain of g. But now you need to pull out anything that would make the denominator 0. And so specifically, I know that 2x plus 3 being the denominator cannot equal 0. And so minus 3, that's going to be 2x cannot equal negative 3, divided by 2, we get that x cannot equal negative 3 halves. And so if I kick out the value negative 3 halves, well, that's going to be from negative infinity up to negative 3 halves, excluding union negative 3 halves up to infinity. And that is our domain. Continuing the same trend, but now I have g divided by f. G divided by f is 2x plus 3 divided by 6x plus 1. But now I have to figure out what can't be plugged into f of x because I need it to not be 0. So 6x plus 1 can't equal 0 this time. And so minus 1, 6x cannot equal negative 1. Divide by 6, that is x cannot equal negative 1/6. And so my domain is going to be all real numbers, remove negative 1/6, negative infinity up to negative 1/6, excluding union, excluding negative 1/6, up to positive infinity. Now if we want to evaluate f minus g of 2, just notice your notes. We've already found f minus g was 4x minus 2. So if it's 4x minus 2, I'm just going to plug in 2 for that function, and that's going to be 4 times 2 minus 2. 4 times 2 is 8, minus 2 is 6. Then f divided by g, we found f divided by g, that was 6x plus 1 divided by 2x plus 3. So when we plug in 2 here, we just have 6 times 2 plus 1 divided by 2 times 2 plus 3. 2 is 12 plus 1 divided by 4 plus 3. That's 13 divided by 7. So 13/7 is the solution. New functions. Given f of x is 3 plus 7 over x and g of x is equal to 7 over x, we're going to find f plus g, f times g, and their domains. So let's first talk about the domain of f and the domain of g. The domain of f says anywhere you divide by a variable, that thing can't be 0, so we divided by x here, so I know that x cannot be 0. And so that's going to be everything but 0, negative infinity up to 0, union, not including 0, up to positive infinity. Then let's find the domain of g, and the domain of g is everything but 0 as well. So that's going to have the exact same domain, negative infinity up to 0, union, not including 0, up to positive infinity. Now we just need to add these things. 3 plus 7 over x, that's my function f, plus my function g. Since it's addition, we can just drop the parentheses, and then I have 3 plus 7x plus 7x. Combine like terms, I have a common denominator of x, that is 3 plus 14 over x. And the domain is the intersection of the domain of f with the domain of g, which is just going to give us exactly the same thing, since from negative infinity to 0, and then from 0 to infinity, where we exclude the 0, is exactly the same for both. That's the answer. So that is, the domain here will be negative infinity, up to 0, excluding union, excluding 0, up to infinity. And if you want, now that we have the plus, we know that that domain is going to be the same for plus, minus, and product. So I'm actually going to rewrite that domain knowing that it's exactly the same. The domain is from negative infinity to 0, union, 0 to infinity. And if I want to find f times g, well, we just write that out. That is 3 plus 7 over x times 7 over x. Then I can distribute. That's going to give me 7 over x times 3 is 21 over x. 7 over x times 7 over x is 49 over x squared. Same functions, but now we're going to do some division. So we already had our domain of f and g. Domain of f was equal to the domain of g, And remember that was everything except 0. So that's negative infinity up to 0, union, not including 0, up to infinity. And now we just have to do the division. F divided by g is 3 plus 7 over x divided by 7 over x. But then remember that we can simplify this thing as it is division by a fraction is really multiplication by the reciprocal. So that's the same thing as 3 plus 7 over x times the reciprocal of 7 over x, which is x over 7. We can then distribute that, and we're going to get 3x divided by 7 plus 7x over 7x, which is really 3x over 7 plus 1. Now, don't think that our domain stuff has changed. Everything that we needed to deal with before, that is the domain of f, intersect the domain of g, and then remove anything that would cause the denominator to be 0. So let's do the intersections real quick. We know those. That's negative infinity to 0, excluding union, excluding 0 up to infinity. But what would cause this denominator, 7 over x, to be 0? Well, there's nothing that would make that be 0, because 7 divided by a number, well, as long as that number is not 0, this thing's not going to be 0. And if you divide it by 0, that doesn't have a definition. And so specifically, our domain is just going to be the intersection of f and g. So the domain of f is negative infinity to 0, union 0, up to infinity, excluding the 0. Now we need to find g divided by f. So g divided by f is just 7 divided by x, all divided by 3 plus 7 over x. Now this one might be a little bit trickier because the denominator this time is not a fraction. So what we have here is actually what's called a complex fraction sometimes. And so if we have this complex fraction, the easiest thing to do is to multiply top and bottom by the LCD of all of it. And so the LCD of everything is going to be this denominator x, and so I'm just going to multiply top and bottom by x. And if I do that, it should clean it up nicely. X times 7 over x is 7x over x, and then that's all divided by, distribute that x, 3x plus 7x over x. Then clean this up. 7x divided by x is 7. 3x is 3x. 7x divided by x is 7. Then when we go to talk about our domain, we just need to look at our denominator, that f of x that we divided by, and I need to remember that that divisor can't be 0. So I need to figure out where will that occur. So 3 plus 7 over x cannot equal 0. So we need to solve this. Minus 3, I get 7 divided by x cannot be negative 3. Then this we can actually cross multiply or multiply both sides by x. It ends up being the exact same thing. So that is 7 cannot equal negative 3 times x, divide by negative 3, divide by negative 3. That's going to give me that x cannot equal negative 7/3. And so negative 7/3 must be kicked out from my initial domain. And so remember that our initial domain is the domain of f intersect the domain of g, but since domain of f and domain of g in this situation were the same, their intersection is of course the same, and so we just need to remove negative 7/3 from that. And so our domain is going to go from negative infinity up to negative 7/3, excluding union, excluding negative 7/3, up to 0, excluding union, excluding 0, up to positive infinity. Now I'm doing this pretty quickly, but if you're concerned about the correct way to write this, put those values on a number line, and your interval notation should match up the number line after you've kicked out the values that won't work.